All right. It's 1 minute past, so I think we can get started. First off, it's amazing to see so many of you here. Now we reached 100. So thank you all for joining. And yeah, let's get started. This webinar is organized in collaboration with Mimmit, Koodaa, and Women in AI. And today we'll talk about how to build AI solutions. My name is Lotta, and I'm going to be your host today. And we have 3 experts from Emblica discussing the topic on 3 different levels: beginner, intermediate, and advanced. Each section will have first a 20-minute presentation, followed by a 10-minute Q&A session, and you can either type in your questions in the chat box or just raise your hand or unmute yourself and speak freely. Also, in the very end, we'll have some time for any additional questions and comments, and I do encourage you to ask as many questions as you can and challenge our experts to really make the most out of today's webinar. And yeah, that's it from my side regarding practicality. So I'm gonna hand it over to Vili, our first speaker. The stage is yours.
Thank you, Lotta, very much for the microphone, although you can still continue to control the slides since Zoom didn't decide to collaborate with me today. But now me and Lotta, we can collaborate instead. So for the next 20 minutes, we will talk about how to build AI applications from beginner point of view. And beginner in the sense of AI development, not in the sense of development in more generic terms. And we will continue to talk about AI applications, how to build them from 2 different points of view, going a little bit deeper in the AI tech and that perspective. But let's get started. So my name is Vili Hattonen, and I come as everyone else here today. On the speaker side, we work in Emblica. Data and AI consulting is what we do. That means that we design and implement AI systems. So not only patch together existing components, but also sometimes go quite deep in the tech and maths, how to put together something custom that is required. But that's about Emblica. Let's go into business. So if mention the fact that we are not specified in the any single modality, so any single type of data. We work with tabular data, with computer vision, point clouds, audio, video, speech, text, tabular data, all kinds of different data sources. And I think today we will face a couple different examples from different modalities, so different data types. But yes, now let's go. So how to build your first AI application. And here is a bunch of questions that we will cover in the next 20 minutes. And with a further ado, let's go at them. So of course, the place where to start, if you think about AI applications, is pictures of plants. So these few captures I've taken on my travels, and I'm not much of a plant identifier. I have to admit that I don't know almost anything about plants, but sometimes when you're there out and about, you would like to know that what kind of plant is this? And would it be wonderful if you had an application that could tell you that based, for example, on a picture or maybe a short video, then the application could identify what kind of plant is this? And going forward, the first question you need to ask is that, is there already an application for that? So after a short Googling, I found that actually from those 5 ones that came up with the quick Googling, the middle one, iNaturalist, is one that promises to identify also animals and not just plants. So let's look into that. I want to have an application to identify plants. And oh my goodness, there is so many observations around the world and so many species identified in this application already. But now the question is that, is this only for me to collect the observations, or will it actually help me to identify those plants? And going forward, then not every application is AI application. So it could very much be that, for example, this particular one doesn't identify those plants for me because I think it's requires intelligence to identify plants. And this says that it crowdsources identifications to other experts. However, going forward, this one is actually an AI application. There is a computer vision model working, and from those hundreds of thousands or actually millions of species, it's promises to be able to identify 55,000. That's already quite a lot. So this is clearly an AI application. And to kind of going forward, then if we want to build AI application, it's a good idea to understand what AI application is. And that's end user software that has an AI component. Okay, simple enough. There's also, great resources for finding this kind of applications that at least claim to be AI app. There's a nice website. There's an AI for that if you want to look around. But that kind of begs a question that, okay, what is AI? Okay, AI application has an AI component. Well, what makes an AI component? Well, if we consider this on this next slide, looking at the species. So it requires some sort of intelligence to identify one. And usually in proper historical terms, we would have some kind of expert that, okay, I show them a picture of a plant, they tell me what plant it is, maybe using them books as a resource. Now, if we outsource this identification process to non-biological algorithm, that is software, and they give us good results, then we can say that that is an AI component, that is an AI system. So then we can define that AI is automated decision-making. We could talk about this a lot more, but for the sake of today, this is what we will deal with going forward. So then now let's say that I have a picture of this interesting creature that is swimming in the sea, and I would like to know what animal this is and build an AI application for that. What would that look like? Then in the next slide, it would be something like this. So I have a picture of that dolphin. I can identify myself as a dolphin, but what kind of dolphin? And then we have some sort of AI component, which gives us then classification, in this case, correctly, that what kind of dolphin that is. And this going forward is like really roughly, you have some sort of input data, there happens some kind of processing by that AI component, and you have some sort of output. This is the backbone of AI application. It's as simple as that. But how to build one? So forward, in the beginner level, what we need to mind about is, well, if on the left side there are these three kind of backbone steps. So you need to have some sort of data. There is no AI without data. You need to have the AI component that processes the data, so does something intelligent with it, and then you have some sort of results communicated to the user. And in a beginner level, we need to have that data set somehow, create or collect it or access it somehow. We need to choose a model that we will use, and we need to present these results or whatever happens to the end user. And we shouldn't actually be building that AI ourselves. That AI system is probably quite heavy to build, but luckily we live in 2023 or future even later than 2023. And there is a lot of services out there that can have captured those AI components for us. So forward, we can use an external AI service that we can plug into. And sometimes these are low code, sometimes these offer an API that we need to just call and it returns something back. And that way we have outsourced the AI component to some other entity. Let's go forward and see where it takes us. So for example, Takomo AI, it's a startup offering a no-code platform for building your own AI component workflow. So here in the screenshot taken from their landing page, you can see on the left images generated with the generative AI models, and then you do some sort of operations to them. You say that, okay, that image goes into this kind of processing, you add a prompt like this, and then you feed it to this model, and then you have an API to get it out. And this is one way of utilizing these AI components built by other organizations or people. Another one is Hugging Face. So this online community of machine learning experts, they have tens of thousands of different models, like actually probably much more. And some of them are hosted, which then you can access through an API. Again, no need to actually do any data science. You just need to know what goes in and what comes out. Okay, and then of course, yes. So now if we want to build the application, then of course we need to have the app somewhere. And there is low code or no code platforms to build your mobile or desktop app, but from the full stack point of view, you probably need to have some kind of application backend. There's the application logic. You need to process the data and then do these integrations to external AI services going forward. Now, this is just like API call, stuff in, stuff out. And again, moving, then this could be like on a really oversimplified pseudocode of the idea of a simple application backend implemented in Python. So you have some sort of library handling your requests, you code some logic, and in this case, process an image, send it somewhere to be classified, and then do something with the results. Basic full stack development. Now, this is a topic for another Mimmit Koodaa webinar, is that how to do full stack applications. I think many of you already have a lot of knowledge about that, but you need some kind of front end, maybe buckled up with your backend, maybe not, and some kind of user interface on the device, desktop, mobile, something else. But here, as you see, the AI component actually from the implementation side is very little. It's few API calls. That means that if we go forward, yes, that what does it mean to our workflow if we are now not building a regular full stack application, but we are building an AI application? The difference is that we need to understand what kind of data are we dealing with. So in this case, click, images. And we want to have images of plants and animals and such. And now in my case, since we are not, I want to get this quickly done and not use any time to develop a model, but use an external service. That means that I probably need a small data set of samples that I can, just test my system with. I don't need to have like a huge data set because I'm not training any models. I'm using pre-trained ones. And then we need to have the integration to the external service. That would be choosing, for example, from Hugging Face, a classification model that has some animal and plant classes already trained with. So it has chance of identifying the objects in the picture. And then we need to complete our full stack application and build the user interface to visualize the results. So the workflow, putting text behind the next magic click is from the AI perspective, it's a lot actually on the design side. Like, what are these going to be used for? What do we want that the end result does? Deciding what kind of data I will use, what kind of data is accessible, where do I get it from? After I know what kind of data, then I can choose the model. When I know the use case, what I want to do with it. After that, okay, what does the model take in? What format do my pictures need to be in this case? How can I access the model, get the API keys and such from ChatGPT and whatever service you're using. Of course, not ChatGPT for pictures in this case. That's why we have a Hugging Face image there. But otherwise, full stack development. And forward as we go, then if you, by this time, I think many of you have already kind of internalized that in a beginner level, building an AI application is that large chunk over there. It's not data science or some higher magic, but actually it's full stack development. So if we click one more time, boom, we can see that a simple AI application where you have outsourced the AI component gives you, if you have been building applications, then the threshold of building an AI application is almost trivially low. Now, this sounds pretty amazing. Every one of us can be everyone who has had some history or experience when building applications in low code, no code, or maybe even hands dirty programming backends and front ends, we can become AI developers utilizing these external systems. However, this does bring some limitations. And now, considering that all the things that we are limited with, we can't, since we are not training any models, we can't really affect the training sets that the models are trained with. This can be a huge caveat. For example, if we consider this example where we wanted to identify plants and animals, you need to have a pretty specific data set to have 55,000 taxas like there was in the iNaturalist example shown above. That has taken actually quite a lot of resources from funders to be able to train and to, first of all, gather the data set and then train that model. We cannot affect that. What if that there is no model available that has all the species that I'm interested in identifying? Or maybe the latencies are unacceptable accessing the external services, or we don't want to be dependent on the costs or related to using these external services. So let's say that I want to develop an AI application, maybe even a startup. I have some goals to make money with some product that is using, for example, large language model like ChatGPT. Now, there is some sort of cost related to accessing that API and making queries there. What if that American company decides to triple their API costs in 1 year? It might take my whole business down if my business model is too much relying on the costs being low accessing that API. So there is a lot of limitations using the external services, but they get you started quickly. Some resources. So if you are familiar with the, for example, doing full stack applications, then I found that the Name My Pet application quite straightforward if you are interested in large language models and good with using ChatGPT. There is really cool kind of instructions on Takomo how to translate and transcribe audio using a Whisper model. And then if you are wanting to go full on Google platform, then without anything, I think that's almost, well, it's at least low code example using that Vision AI API. which you could actually use to build similar application than we were discussing today. But I think I want to end up with this really kind of controversial observation that not every application is an AI application. I think this is 2 days ago, this media outlet is setting news out about software startup that actually the founder made it to Forbes 30 under 30 list, is using humans instead of AI, making 2D sketches in the 3D modeling, even though they claim that they have AI that makes 3D modeling. This is a really extreme example, but I think this underlines the limitations of AI models to generalize to every single possible use case. Like, it is not that simple as you think. And sometimes that means that the ready-made solutions that are available are not ready to solve your use case. And for that, you need to have more advanced techniques, like we are going to hear in the next speeches. But yes, okay, it was enough on the beginner level. It's full stack development using external services.
Okay, thank you, Billy. That was really, really insightful. Now we have a few minutes for any questions. You can just type it in the chat and I can read it out loud, or Billy can. And also, if you just want to unmute yourself and talk out loud, that's also possible.
Yes, please do ask, because covering a topic like, okay, how to build AI applications in 20 minutes, you probably have something specific that wasn't covered in this first take on the beginner level.
Hi, so my question is about the tech stack. Like you said, 80% is the full stack development. So what tech stack would be most better for this kind of application?
Yeah, so if I heard correctly, then what technologies is it mostly in that full stack development? Well, it's really depends on your use case. If I would build kind of like, okay, I have 8 hours to build AI application, then I would probably use Fast API and Python because of my history as a data scientist. I worked a lot with Python, and that would get me going really quick. I would set up backend. I would use something very simple to visualize the front end. Have probably, for example, in this example that we used, recognizing species, and you would just need a place where to drop your image and another one to kind of display, okay, how it's classified. And on the backend side, then I would just make my API calls in Python using the ready libraries, and that's that. But it's definitely not the only option. You could make the same in JavaScript. You could do this Ruby on Rails. There is almost all high-level programming languages have very ready-made libraries to get this kind of full stack project started. So on this kind of beginner level, since we are working through those application programming interfaces, APIs, it doesn't really matter what technology or languages you use to implement your full stack application. From the point of view of like getting started. Of course, then if you go into production environments and such, then there comes requirements with those. Something to mention is the hosting. So that application needs to live somewhere. Ruby on Rails or Heroku have solutions of hosting applications kind of inbuilt. And if that's the lowest threshold you want to, put something online, then use that. But of course, if you want to go a little bit more fancy and then scalable in the future, then putting hosting things on AWS or for example, Google Cloud, maybe even in Docker containers, will give you a lot power and flexibility for the future development of the application, because I promise you, after you made the first version using the external AI service, after you used it for a while and you notice that it doesn't work perfectly and you want to maybe go a little bit deeper on the AI side, then having more control over the hosting becomes relevant.
Thank you. Yeah, we have a couple of questions in the chat. Is there a low-code way to create AI applications?
Yes, there definitely is. There is at the moment, there is tens of platforms. And now I made a conscious decision not to promote any single one of those because the landscape at the moment is changing a lot, and we don't use, at Emblica, we don't use this kind of low-code platforms because it doesn't give us enough control on what we're doing. Therefore, we don't have this week's insight because the landscape is changing rapidly. But if you do a little bit of Googling, I'm sure that you find platforms for drag and dropping. And if, for example, the Takomo AI, that actually is in kind of like doing that AI AI component pipeline of like, okay, let's generate let's give a prompt to a large language model, which then gives the solution to this image generation model and so forth, and you want to make this kind of pipeline. The Takomo AI is a no-code platform for making that. Now, the easiest way to start, I would probably, it depends if you have full stack background or not. I would personally build the application myself. So, for example, JavaScript or Python, set up your first backend, look tutorial from the internet how to get your full stack thing going, and then access that external AI service that I talked about a lot. But there is also an option to do the low code, no code approach. For example, well, now I'm going to mention names after all, but for example, Airtable has APIs that allow customization later, and they have, I believe, that some AI features already like easily accessible. So that is one way to approach it. It really depends. What is easiest depends on your background. If you have programming background, make a full stack application like you have before and attach AI service. If you have no code background, then search for a low code platform with a good customer or user support and a good community, because then when you run into problems, you will have someone to help you out.
Thank you. Yeah. Any other questions at this stage? Nope.
You want to click the next slide?
Yes.
Yes. So not the Q&A, this one. Yes.
Yeah.
So because this is what stays the same, it doesn't matter if it's low code or full stack. The workflow with the AI application backbone is the same. You need to have the data, you have an AI component, and then you get some kind of results that you need to communicate to the end users. But as said, this is very limited. You are completely relying on external services that you have no control over, and this brings you a lot of problems. And maybe Venla can tell us more about how to tackle those troubles.
Yes. Okay, it's time to move forward. Venla, the stage is yours.
So, hello everyone. I'm gonna take stage for this intermediate presentation and maybe dive a bit deeper with actual data science stuff and not focus so much about in this full stack thing that Willy was talking about. Let me see, how does this work? Chasing the slide. Yes, and more specifically, we are talking about using existing models and customizing them a bit for our problems. And we are gonna talk about building a good quality data set and fine-tuning the model. And yeah, my name is Venla Viljama. I work as a data scientist here in Emblica. And good to see you, or good to know that there's a lot of people listening. And here's the agenda. We are going to talk about what are the pre-trained models, or what is fine-tuning them, and why do we want to use pre-trained models, and a couple of tools that are useful when dealing with these models or skills. And then what kind of components there are in this intermediate level compared to this beginner level. And then the main thing is focusing on this workflow, or how are things usually, in what order, and what does it take to collect the data and fine-tune the model, train it, evaluate, and decide when it's ready, and so on. Okay, so why do we want to use existing models? We don't, of course, if somebody has done a model, we don't want to reinvent the wheel if we can use that. So what is pre-trained model? Basically, the saved weights of the network, usually trained with large amounts of data in different data domains. So different data domains have different kind of models. You can either use the model as is, like Willy was telling you, or you can reuse it in a way that you train it to, or use your data set and train it to some kind of closely related task. Or the thing that we are focusing here is fine-tuning the model a bit. For example, if we have a general model for object recognition, we can fine-tune it to detect some specific objects. And in that case, you might need to do something for the model, freeze some of the layers, maybe add a classification layer or something like that. Some examples, and like Willy already told you about Hugging Face, I have also linked it here. Many of these models can be found in Hugging Face. For example, for object recognition, there is this YOLO, you only look once, which is our example in our example case. SAM comes from segment anything. You might want to check those out. For image classification, ResNet is a really popular one. In natural language processing, we have traditionally there is a lot of versions of BERT, which is transformer-based model architecture. For example, there's FinBERT, which is for Finnish language. Llama is one of the newest ones, popular large language models. And there's also these multimodal pre-trained models, for example, stable diffusion for text to image. So there is two modalities of data. And what are the benefits? Basically savings in many ways. So in time, we don't have to build the model from scratch, design the architecture. We don't have to use time for that. We don't have to use the time for training the baseline model. And when we don't have to train it, we also save computational power, which lowers the carbon footprint, which is good for the environment, or better than training from the scratch. Also, there's no need for so advanced skills, because you can use something that somebody has already done and they have the knowledge. And there's plenty of tutorials available for this kind of fine tuning. So it is easy to get started. Yes. So here is a kind of a short list of some of the tools that, for example, I usually work with or face with in projects like this. Python is pretty basic programming language, and Python has many of the libraries that we use. Pandas and NumPy, for example, for data processing. There's OpenCV for making computer vision tasks easier, FastText, and NLTK for NLP tasks. You are most likely going to face PyTorch and TensorFlow, which are open source machine learning frameworks. Makes my life a lot easier. Cloud environments are useful. Many of the tutorials are in Colab notebooks. AWS SageMaker is another place for training your models in cloud environment rather than using your own computer. Of course, you need some kind of editor. I use VS Code a lot. And also one useful thing is to get familiar with terminal or command line tools, because oftentimes you train the tutorials tell you to train the model with a command line interface. So knowing a bit about that is useful. Okay. You remember this slide about components in beginner level? There was a couple of boxes. And in this case, when we are training or fine-tuning our model, we need a couple of more steps. For the data, we usually have just raw data, and we need to process it quite a bit, annotate, convert, split, and so on. We are going to dive deeper into these steps later. For the AI part, when you're training your model, you need to choose hyperparameters and actually train it, evaluate it before you are happy with your model, and then you can host it and visualize the end results or user outputs. And the typical workflow is the one that I'm going to present to you. It either starts with data or the model. Sometimes you don't have the data, you just have the problem, and you look for suitable model for that, and then you start collecting the data for that. Or then you have the data and you need to find a model that suits that. Then you do all the steps for the data training process, and since it's never good in the first loop, then you have to iterate the training process a couple of times and host and have the end product after that. Okay, but how do we choose the model? First of all, we need to have a problem that is that can be solved with machine learning, and knowing your data modality narrows down the options quite a bit already, of course. And task is the other thing. If you have a classification task or some other task, then there are different models suitable for different tasks. Also, what do you want to look when choosing the model is what kind of inference there is available for that. Is it easy to implement? Is the tutorials for that? Because sometimes you end up in a situation where you have been dealing with one model for quite a long, and then notice that there is this and these problems with the API, for example, and might want to change because of that, if it's possible. Then when you're loading the model, maybe start with a small version of it and see if everything works well with that training process first iteration before moving to larger ones. And when we are fine-tuning, like I already mentioned, we might want to modify the layers if needed, freeze some of those and add layers if needed. Or there are different techniques of that. We're not going to go too deep in that in this presentation. Yeah, let's have an example. Let's say we want to detect those leg bands, tiny rings in bird legs using images. So our data modality here is images, basic RGB images, and the model we might want to use for this is this YOLO, newest version of it. It's a single shot object detector. Intuition behind it is that the YOLO comes from you only look once. Like the intuition is that the model processes the whole image at a single pass. Some of the models first detect the presence of the objects and then the location of the objects, but this one is doing it in a one pass and it makes it faster. Yeah, now we have the model. We might want to build the data set next. When we are fine-tuning, we like tens of samples might be enough in some cases, but more the better. So I would say that if you have hundreds and thousands or thousands of samples, that is good. Good starting point. You want to we want to pay attention of the quality of the data, of course, if there is enough pixels and the like distance where the pictures are. If you are talking about pictures, are the distance that the pictures are taken is good. Also that there's enough variety in the data and the samples are valid for the task that we are talking about. Balance is also one important thing. If you have, for example, two label classification, you might want to have 50-50 balance. There are techniques to improve the, at least the like if you don't have enough data, you can have more data with simulation or augmentation, and Samuel is going to talk about that a bit more. Cleaning is an important step, removing bad samples from the set. For example, in NLP, you might want to remove the words that don't really mean anything. So, for example, articles to make the results better. And of course, annotating. So that can mean, for example, segmenting the objects from the image, drawing bounding boxes around the images, labeling images or text or anything like that. In text, more generally or more specifically, you can have tags like a part of speech tag, if the words are verbs or adjectives and so on, or named entity recognition. So tag all the names. And after that, we need to convert, depending on the input format of the model we are using, convert the data according to that. Okay, let's check our example case. So when we're collecting the bird samples, bird images, we want samples both with the bands and without the bands. A source can be, for example, internet, or we can set up a photo shoot in those bird banding events and control the data quality at the same time. And then for annotating, I would use this Label Studio tool, open source tool. There are other tools also. Basically, just draw this rectangle around the bands, maybe include a bit of the bird's leg to give it like a context. And when converting to YOLO format, this is one example of a format. There is, for every image, there is also a text file which tells the label and the coordinates of the bounding box. That is also, for example, Label Studio does that automatically. Yeah, now we have built a data set. Before we get into the training, one important part is splitting the data. So there are 3 parts that we need to form from the data: train, validation, and test set. The ratio between those can be, for example, 70-50, 15-15. Really depends on the amount of data and task and model and so on. There are, I'm just going to mention here, there are techniques for small data sets like cross-validations that improve the results. And yeah, so what are these? What are the functions of these different data sets? Train set is usually obviously used for training. So model learns from this data and improves the parameters of the model. And validation data set we use to evaluate the model and adjust it for, so before every retraining we check the model against the validation data set, and goal is to find the optimal set of parameters for optimal results. And about test data, in training loop you should never use this test data. This is to evaluate the final performance and to make sure that the model doesn't overfit. And I'm going to mention that again later. Okay, now we have data sets and ready to choose the hyperparameters for the training. What are the hyperparameters? They control the learning process. You choose them, like I said, before every training loop. And it really depends what kind of parameters you have. It depends on what optimization algorithm your model has, or what do you choose, what loss function you choose. But here are a couple of the most common ones that you're definitely going to face. Learning rate, it controls like how big steps the model is updating the weights in every loop. There are some starting points to use for that. Epochs, how many like number of epochs you are training the model. So how many iterations you pass the training data through the model. You can, for example, start with 3, scale up from that. Other parameters are batch size, weight decay, dropout, so on, just so that you know that these things exist. Method how to choose this in every training loop, trial and error, basically. There are grid search, random search methods where you set up, where you choose sets of values for these parameters and then train with those. But the more you do this, the more like a hunch you get of what are the best values to start with and how to continue from that. And yeah, when we have set of parameters, we can train. And training means that you update the weights of the model according to the parameters you choose. And in practice, training means that you just run the training command, and that's what updates the model weights. And then we get to the evaluation part, and in this part we deal with this validation data set. So we run the model or give the predictions for the validation data set, and then we compare them to true labels, so the correct answers. One of the like most used ones, or at least for me, in almost every project, we first print out the confusion metrics, which compares or gives the counts of predicted labels and true labels against them, or corresponding true labels for them. And these true, positive, false positive, and so on values are really useful for other metrics, evaluation metrics. One everybody has heard about accuracy, which is fraction of correct predictions. So your accuracy can be, for example, 90%, which may sound good, but there is problems with this one that you should know. For example, if your data is not in balance, 90% ratio, 90% accuracy might mean that your model can only predict one label. So it cannot, for example, predict any negative values, negative labels. So be careful with that. But good thing is that we have many other metrics to use. Here are just mentioned the most popular ones, or some of the popular ones: precision recall, and F1 score, which is kind of a combination of precision and recall. For all of these, there is a formula which includes these true positive, false positive, true negative, false positive values. MCC is just dropped it here. It's really good for binary classifications where the data is really imbalanced. And a nice thing to do is print out these metrics and plot some of them to compare the results in every training loop and see how your model is evaluating and how it's how it's performing in every training loop. So that gives you a hunch of how to maybe modify your hyperparameters. And now the last question: when is your model ready? How do you know that? For that, of course, you want to check the evaluation results, metrics we talked about, and also loss convergence. Samuel is going to explain more about what is loss. Basically, it's like a penalty between predictions and ground truth values, and you want to get it as low as possible. But when the loss starts to stay in the same level, so it's not decreasing anymore, that is a good indicator that your model is already pretty good. But there are also situations where, oh yeah, and we are talking about validation loss here. So comparing the using the validation dataset for that. There is also training loss, and in situations where training loss is getting lower, but the validation loss is maybe staying in the same level already, it doesn't really mean that your model is getting better. It might mean that the model is overfitting, so it's learning too well to fit in the training data, but it will not perform really well in the, for example, in test data or the data that it has never seen before. Okay, now and in this case where we have this overfitting plotting, it might have been a good idea to stop the process in say about 70 epochs or 50 epochs. Okay, that was the workflow example of fine-tuning the model, and Samuel will maybe tell what is the difference between this and if you had to do some extra steps if the dataset is not good enough, or if you need to modify the model or even do your own model, make your own model. here are some of the links that might be useful, and yeah, if there's any questions, now it's time for that.
Yeah, thank you, Venla. Really interesting. So we have a few minutes for any questions. You can just type the questions in the chat or unmute yourself and speak out.
The pressuring silence of everyone thinking, could I ask? I have a question. What do you, Venla, do you think that, well, I wanted to have the species detection model. Do you think that this kind of fine-tuning would work? What model would you use?
You had a YOLO example there, right? Also, or
Yeah, I mentioned.
yeah. I think you know the answer better, but if you would, yeah, in my example, we fine-tuned YOLO for one, actually, or two label classification. So at least maybe not that, at least not in the same way. How about Samuel? What model would you use?
Oh, sorry, for what?
For
Getting my species. I want my species detector.
What model?
Like, is it possible with this intermediate way of like fine-tuning, or do we need to make a new model from scratch? What do you think?
No. I mean, I think the YOLO is a good example if you want to make it fast, but then you can just like use the ResNet backbone and train a classifier head on that, I guess.
Yes. Right. So
you would
yeah,
need quite many labels or classes.
Because I think using the kind of beginner tools that we discussed, it is not possible to make a species detector that would recognize those mangroves and dolphins. But I think some ready model, pre-trained model, fine-tuned in this intermediate techniques that Venla just talked, maybe would be suitable for that, and you don't need to design and train your own backbone model.
Yeah, we have a few questions in the chat. So how to choose the right tool for building applications, because there are so many good ones. Can we get a quick answer to this one?
Well, since I was talking, I would probably see how widely used it is. Like, there is a lot of tools and a lot of software, a lot of communities look. If there is a large community of users, if there is a large like support, a lot of cases of bugs they've been resolved, because you will run into problems, it's guaranteed. Now the question is that, do you have support solving those problems? How mature is that tool that you're looking at? The tool could be now anything. So I think the kind of how popular, how large the community is, that's a big factor. And then just see that it actually solves the problem that you're looking at. So reading the docs, seeing the use cases, does it match actually what you want to get achieved? Was there something else on the chat?
Yeah, so what does the MCC mean in one of your slides?
Oh, it's wait a second. Matthew's coefficient correlation or something like that. Also called phi coefficient, but like I mentioned, it's a good tool for or good metric for evaluating two class or binary classification where the data is highly imbalanced.
So basically, if you have a lot of pictures of birds without the ring in the leg, and then you only have a few pictures of birds with the ring, then that could be a good tool.
Good one. I will add a link to that mention.
Thank you.
Yeah.
Okay, a couple more quick ones. How about an AI chat API? How would you go about to set a certain tone or goals for it?
This depends a lot on the what you want to achieve. So talking about large language models, as we know, that's a really new field, and they have a lot of problems with jailbreak and this kind of tones and goals. has been a lot of trial and error with the prompting. So idea is that you have a large language model, maybe you have even hosting it and you fine tune it with your own data set. And then you prompt it certain way always prior to the user interaction. So for example, you can tell it to, okay, act as kind caretaker. And then you leave it for the user to have a chat. But this is really sketchy. Like, I wouldn't trust it. There is so many ways to break these kind of promptings. Even if you try to, like, all these examples over the internet, how the ChatGPT and others have been made to prepare napalm and all kind of other kind of things, that they are saying things that they are supposedly prohibited. It's a tricky path to take. So there's ongoing research and trial and error, but I wouldn't be holding my breath for a solution that, solves it. I think it's going to be like cat and mouse of like, okay, someone invents a way of prepare the large language model properly, then someone invents another way to break it. And this will go taking steps. So I'm not expecting to have a solution that is completely reliable anytime soon, or maybe ever.
Okay. We have a couple more questions, but I think we will have to move on to Samuel's presentation, and maybe Vilja and Venla, you guys could answer the questions in the chat.
Yeah, let's do that.
Or we can get back to them after the next presentation.
Yeah.
Let's go.
Thank you, everyone.
Give us someone.
So let's start again. So previously we have been looking at either a low code / very easy to use pre-trained machine learning model, or either we're looking at some fine tuning when we have some great data set available for our task, and we have this kind of optimal situation in this machine learning problem. But often we have this issue where we have some great problem we would like to solve, but there's just not enough data available. And we have maybe some 10 to 100 samples, and this is not enough for the model to truly learn the problem we wanted to learn. So the topic for this final presentation is kind of deep learning in low data environments, where deep learning is this machine learning everyone wants to do nowadays. It's this neural network architecture we have been focusing on previously as well, but it's under the umbrella of machine learning, of course. And my name is Samuel Piirainen, and I'm also data scientist at Emblica. So first of all, we kind of measure the importance of data here. So these state-of-the-art machine learning applications that are pretty much always done with deep learning methods are very scalable with the amount of data, that is assuming if your training data is good. So as we were talking in previous parts, the data has to be varied enough, but it has to be from the problem distribution we want to solve. So if we have this kind of good training data available and lots of it, the model can probably be solved with some quite a generic method, like we take, if we have object detection challenge task or object classification challenge, we take a ResNet and train a classifier on top of it and fine-tune the classifier. So more data can often solve the problem. But this also means that the lack of data, you can often perceive it as the bottleneck in solving this problem if you don't have enough data. And you can just be like, well, I don't have enough data and my model doesn't learn enough, so I need to collect more. But collecting this data can be very time consuming. It can take months, it can take even years if it's some really difficult problem in some cases. And also it can be quite expensive. You might need many man hours to do this collection task. So advanced tools and expertise in this field gain lots of value inversely proportional to the amount of good data we have available. There's this nice plot as well, but that kind of illustrates this. I drew. It's kind of hand wavy, but it sort of holds true in most cases. And here are some common tools to mitigate the issue, of which we will focus on these two because these are all quite large topics to discuss. So we will take a look at the data augmentations we have mentioned already before, and then also kind of model architecture, in particular the choice of loss function here. It's one of the model architecture concepts. So first, the data augmentations. Well, firstly, where do the augmentations fit into our great workflow here? We will augment the data after it has been collected and it has been pre-processed. So we have this nice pre-processed uniform data set that we do augmentations on, and then after they have been augmented, we feed this data to the model. Now, what does augmentation mean? Well, it means quite simply just that we transform this data such that we end up with more data in our data set. And kind of the intuitive way to look at this, or the practical way to look at this, is if we, for example, have this picture of this cool astronaut here, and we want to maybe detect the job. We want to do like this for some reason. We want to make this model that knows that learns what job this person is working in. So we want to know that we want to teach it that this person is an astronaut. So we can use transformations to create more samples in our data set that are slightly different from the original, but they are still from the same class. And this way we end up with in this example, 5 times the amount of data, where each sample is kind of a permutation of the original. For example, we have on the second picture from the left is this kind of shaken version of the real sample. And this is great because it helps the model to understand that in real world, we often, in real world, the picture is often imperfect. We don't have like a perfect version of this thing we're trying to teach it in real world. So the model learns here that it needs to generalize to imperfections in the data. And the nice thing also about these augmentations is that they are very easy often to automate in your programs, in your actual program code. And these are often found in ready-made libraries like the PyTorch or TensorFlow we were talking previously. They have their own set of augmentations. You can just like fire at the data in your code, and there's often not much you need to do to increase your data set size like this. And well, the thing to note about augmentation also is that they are great if you choose them well for your problem, but if you have a bad set of augmentations, they can actually also just slow your training down and confuse the model more than actually teach it anything. So you have to be smart about how to choose them. And it depends really on the problem. So in image domain, for example, this kind of blur or flipping the image around or rotating the image or changing the colors of the image a bit, this makes the model generalize to different pictures of the same astronaut in practice. While in the audio domain, you have to think a bit different. So in audio, it's not quite as intuitive. In audio, we can, for example, look at the spectrogram of the audio, and we can remove parts of the spectrogram so that the audio becomes more lossy in practice. And this also makes the model generalize to imperfections in the audio file. This is great for speech recognition, for example. So that's one trick. That's probably the first thing you want to look at when you don't have enough data available. Then there's the model architecture part, which is not directly related to your data set. It's more just about making your training more efficient, so the model understands the problem easier. And that's the choice of loss function. And this kind of fits into our workflow. Instead of choosing the model, we want to redesign the model a bit. So usually if your model has been trained with some loss function, we may want to try another for it instead. Well, what is a loss function? The intuition, non-mathematical intuition, is that it answers our model, how did it work out? And this is it's just a guide for the model during training in this sense. And this answer can change depending on our grading criteria. So if you've ever been in school and you have done some tests and you haven't been happy about the test result, and you say, well, the teacher graded this exam very wrong, I don't agree with this at all, then you may be in the same situation as some model that has been trained with a poor loss function. So yeah, the loss function choice changes how the model perceives the problem as being solved. And this grading criteria, the loss function, are in practice formulated as a mathematical function, hence why it's called a loss function. So from mathematical perspective, we iteratively optimize the model to approximate some target function by minimizing the loss function. This kind of mathematical jargon, but it's one way to look at it for sure. And a kind of funny sneak peek into the learning process of a simple model here is, here's this video I found a while ago. And what the model is trying to do here is to separate these two sets, or rather there's this data set where we have yellow and blue points. And the objective of the model is to separate the yellow points on one side of the video and the blue points on the other side of the video. And as I started this video, in the beginning, these samples will kind of jitter from one side to another as this iterative learning process starts going on. And then eventually they will kind of find their places on each side. And then at the end, the learning process will stop as the model has converged to some great realization of how this should be. So now it's jittering, and the model is trying to figure out the positions. And now these two sets of classes are on each side, but they're still jittering as the learning process is still going on. And there we are, it finished. It was quite fast in this video, but in practice, it's obviously way slower. There's just a very simple example of this to kind of give you a feeling of how it learns. So where do we start with these loss functions? There are very many options, and many of them are also derivatives of each other. But we have some very archetypical loss functions that are used in many tutorials or in the scientific literature. And in a classification problem, the one you're usually first taught is the cross entropy. And it's a great loss function because it suits most problems well because of its very generic definition in mathematical terms. And it also has no hyperparameters to tune, which is awesome because the less hyperparameters to tune we have during training, the simpler that makes discovering the optimal hyperparameters to begin with. We already have enough of those, as Venla kind of showed us earlier. And the cross entropy is well established in literature, so it's a great baseline to compare other perhaps derivatives of the cross entropy loss against the cross entropy itself. And first of all, to kind of understand what cross entropy is, we have this simple visualization here where we have two functions. We have the function p and the function q. And on the picture on the left, these two functions are very different from each other. So the green function is on the left side and the blue function is on the right side. And there's this metric called relative entropy that measures the difference between these two functions. And the relative entropy is quite high here. So it's 2.5 over, peaks over at 2.5. And as these two functions on the right side image move closer to each other, we could say that p approximates q. So they are approximately the same function. Now the relative entropy is quite low. It peaks at only 0.05. So we have a kind of approximately the same functions. And this is actually what we're doing with cross entropy. So the mathematical definition for cross entropy is that given a target function p that we want to reach, and the approximate function q, which is actually our model we're training, we want to minimize the difference between target function p and our model q. And this is what we're doing. So we want to make the model be closer to some target distribution of this data. The target is actually our training data. This is kind of, again, a mathematical jargon, but if you really think about it, it makes a lot of sense. But cross entropy is not always perfect. And this kind of brings us into the topic of when do we want to change our loss function or consider alternatives. So we have this example of problem that we want to learn to associate some image of an animal with the name of the animal. So it's like an animal classification problem. And cross entropy works very well here most of the time. So, you know, a horse looks very different to a crocodile. So it learns to classify these two animals very well. It never would confuse a picture of a crocodile into a horse. But if you think of a tiger, for example, a tiger is quite similar to a cat. So maybe our model with a low amount of data available would confuse a cat with a tiger, because cat is just a smaller tiger. So, and here's on the right, we have this 3D representation of how the model has learned when we have used cross entropy. And in this actually just illustrates this problem I was just talking about. So the model thinks tigers are this red kind of clump in this 3D space, and the cats are this pink clump or cluster. And these two clusters are very close to each other, which means that when the model is predicting some picture of a tiger, it's actually quite likely that it will discover it as a cat instead, because these two clusters are so close to each other in the mathematical view of this problem. Well, how can we solve this? Well, we can assign each of these clusters a safety margin that they at minimum must be from each other within this 3D space. And this can be kind of built on top of the cross entropy loss, where we tell the cross entropy loss that there has to be a minimum distance for each of these clusters it's classifying to be from each other. And here's this margin kind of drawn in 3D space. So it's this green angle between the clusters. And as we do this, in this picture now on the right, the tigers and cats are very well separated because the margin exists there, and the clusters are tight and far away from each other. And this kind of loss function actually has a name. It's called the arc phase, and it's a very well known loss function in the task of facial recognition, for example. And well, why facial recognition in particular? Well, if you think of facial recognition, even the most far apart faces are still very similar to each other, at least from the perspective of deep learning model, it turns out. So the model has to figure out very small details that separate a face from another face. And the arc phase happens to perform here very well because it forces each phase to have this safety margin in this 3D space. So this loss function we have now constructed is very good at maximizing the between class separation while minimizing the within class separation. So the clusters are tight and far from each other. And this means that our model is no longer mixing up tigers and these big cats, perhaps, which is great. And here is again the kind of advanced workflow. So we have added the augmentations after the data pre-processing. And then there's the model redesigning that happens perhaps at the beginning. Then it happens after we have trained a few times. We try how the model works, then we have to maybe refactor the model a bit again. It's a very can be a long process until you find the perfect combination. And we actually have a workshop coming of data augmentation at Mimmit Koodaa, where we will look at all kinds of augmentations in practice. That's going to be fun. Augmentations are very fun to play with, to figure out what's a good selection for some problem. And now some questions, if you have any, that is.
Yeah, thank you, Samuel. Yeah, we have a few minutes for any final questions or comments. Let's see.
Again, everyone is busy writing and thinking, can I talk? Well, in the meanwhile, everyone is writing. I will. Samuel, can you go back a couple slides to the big picture? That one, yes, advanced workflow. Sorry. So what would you say that as a data scientist, when you work on a project where you can't use an external service that would have the model ready, or even just having a ready-made model and then a little bit fine-tuning with your own data set, like Wenla was talking about, it's not enough, but you need to do these advanced methods that you explained. What takes the most amount of time? Like if you would point out from these boxes, what do you say that would take, I don't know, the 80-20 rule, that what 20% of the tasks take 80% of the time?
Yeah, well, it's certainly working with the data. It's the red part of this diagram. So we have to make sure that our data pre-processing does every step correct. It's actually surprisingly easy to mess up something during even pre-processing and maybe use some wrong data type somewhere, or you're pre-processing the data so that the picture becomes a little smaller, but then you use some wrong interpolation for resizing, and that fucks up the pixel values or this kind of stuff. Sorry for my swearing. And then also figuring out these augmentations. You really have to think of the problem and see what is the good combination for your problem, because sometimes it's very easy to actually do an overkill with these augmentations because you have so many of them freely available, and some very big combination of these can actually make the problem even worse. So you have to start simple and then slowly add up more augmentations until you find the optimal position.
Yeah, because when you do augmentations, you get more data because, by definition, you are taking one sample and augmenting in different ways, and then you have more samples. But when you get more data, you also get often more difficult data samples, which is one way good because your model is maybe, if it learns that difficult augmented data, it's more probable to generalize to data that it has never seen, and it will see when the application is used. But at the same time, if you do too many augmentations at once, then maybe the model cannot learn anymore at all. And then suddenly everything is broken.
Yep.
Yeah. I also have a question. As data scientists, what do you guys think is the most interesting thing when it comes to building AI applications?
For me personally, I think it's actually just you try all of these different combinations, let's say we combine augmentations and we select hyperparameters, And then we put the model in to train, and then we have some great visualization software, obviously, that shows during training how the model is learning. We have the great metrics we have chosen, and that stuff. When you have that ready, and you see how the combination of all of these things we were talking about, how it affects the model learning, I think that's very interesting to see in practice. But maybe it's different for Venla. I don't know.
So what is the most interesting part?
Yes.
Yeah, I guess it's the same. It depends on the model and on the problem we're working on. I am really interested in NLP, natural language processing. So maybe having a model and checking that how does it, for example, see the word vectors, or how does it understand the sentiment analysis of the text. That is one of the most interesting results. But yeah, in big picture, the same thing, seeing how the model learns and seeing the results.
Yeah, it's interesting when you have the combination of different pre-processing, different augmentation, different hyperparameters, different training schemes, different model architectures, different loss functions, like different data sets, different splits. Like there's so many different combinations when you change this all that you absolutely cannot try everything. So then kind of figuring out that what will work and having these educated guesses of trying to understand how the models see the world and see the data, and then when you get that right and you get actually something working, that's really, really satisfying, and you feel like doing some sort of voodoo. And that's actually the part where you need to. So for the beginner level we discussed today, you don't need almost any data science experience. You need to know what kind of data you deal with and how to format that to send into that external service. In the intermediate level, you need to understand a little bit better. You need to be able to maybe fine-tune the model, choose hyperparameters for retraining, and to maybe process the data a bit. But here in the advanced level, there where you really need the math. So in order to design your loss function or understand that why some loss function doesn't work, you need to understand the deeper mathematics, because that will define how the data is transformed for the model and how the model kind of sees it and how you're going to give feedback through that loss function. So that is, and of course at Emblica we work at this advanced level. Sometimes we might have a project where the intermediate is enough, but mainly we operate in this advanced sphere. There's a good question from Heta about the data augmentation training model. At what point do you run into the problem that the data is no longer moored to real life examples? You often run it actually by default. When you augment your data, it's going to be something else than what is out there. However, just the sheer fact that's not necessarily a problem, because sometimes just showing more drastically different examples where the signal stays the same, you're just basically applying different kind of noise around the signal. So let's say we want to detect the rings from the pigeon foods that Venla was talking about. Sometimes having more drastically different images that you will never see in the real world will still while the ring is still staying there, will help the model to generalize better to the real world, because it becomes more persistent to the noise, as long as the signal is relatively unchanged. That is the ring in that picture. I don't know if I managed to make any sense, but that's my short take on the really good question.
All right. Yeah, I think it is time for us to wrap up. So thank you everyone for joining. As mentioned, the slides will be shared as well as the recording probably during next week. And if you have any questions later on, or you want to talk about AI applications, you can reach out to us, for example, through LinkedIn. And hopefully we'll see you during the next workshop mentioned before.
Excellent. And the workshop is in person at our office in Helsinki, and hence it has very limited spaces. So once the sign up is open, then fast will be first come, first served.
And
Absolutely.
be sure to follow, for example, our LinkedIn and Instagram to give the notes about possible upcoming events and news. And thank you
Excellent.
everyone for coming and listening.
Yes.
Right.
Thanks from my side as well. It was fun.
Thank
Thank-
you.
Great time.
Yes.
Have a nice weekend.